Testing. Does this mic work? Dear viewers, sorry about the previous video. I'm really pissed about losing the audio in it. OBS, which I'm using to do these screencasts, will from here on be known as Check the Mic. I literally renamed the shortcut to that. The stupid thing randomly keeps switching from the mic that I'm using to the default input device, which doesn't take in any audio. This happened to me a few times before. And this was the previous video. It was a really difficult subject, so I didn't want to bother with putting stuff into DaVinci Resolve on the timeline as I go along. Instead, I wanted to do everything all at once and then edit it afterwards. So you can imagine my shock when I opened the video and there was literally no audio on every single clip. So to make up for it, what we are going to do is a review. It might be good to do that, since nobody would have watched the 16 hours of me live streaming the GADT implementation. What we are going to do is start off with an explanation of what the GADTs are to begin with. And it's going to be a lot easier to explain now that the language actually has that feature. So what are GADTs? In a word, they are specialized unions. In contrast to regular unions, which can only have very generic constructors, regular unions, GADTs, can have specialized ones. And what this allows us to do is something that needs to be demonstrated. Let's open the Spiral compilation tests, and I'll show you what they are on the very first example. Ignore this for now. And take a look at simply this. They are written with a double colon, and they can take an arbitrary amount of arguments, and they have to end with an instance of itself. For example, if this wasn't union T but union QA, if we rename it, then we get a type error, unbound variable T, and it also says that the GADT case in the union has to result in an instance of the union being constructed. Any other type, any type other than the self being in the range of the union is not allowed. The range of a function is just this second argument. And if we rename it to QA, the error goes away. So it's a bit like how you can have a regular union. Let's suppose we have an option type, union option T, and then we have the sum case, which is X. Which is T, and the null case. And then we could go ahead and write something like a constructor for it, make sum. And then it takes in, first it needs to be a for all, it takes in a T, and then it returns an option T. And in this case we can just pass it to X. So, and suppose we also added some. Sorry, I want to say that this is like how it would look like if you wrote out the constructor out in full, and you can write that explicitly in the union itself now. For all T, and then T option T. And these two are equivalent. Except when you write in a GADT case, the compiler has a lot more information. Suppose you had something like another case, old. Let's make it old. And we can make it int option int. And ordinarily, with just the capabilities of the previous unions, something like this would have been impossible to write out. You could write out something like a function, like make old int. You could make a function that acts as an alternative constructor to this, but the compiler wouldn't do anything with this. Suppose we wanted to destructure this alternative option. Let's just disable all this. Let's make it G, and then it takes in for all T option T. And then suppose we match on it with some x, and then we have the alt x, and then we have the none. And for the none, we're just going to throw an exception. Try to unify the type variable A with a metavar outside its scope. Yeah, I'm really glad to see this error, because I never actually tested much of the GADT capabilities. So what we need to do to fix it is provide an annotation explicitly. And now, if we call our A, you'll see that okay, arguably, what I wanted was to see here would be. I mean, what I would have wanted on the type cover would have been to see the type variable T. Suppose we try to coax the type cover to do something like this, and we hover over it, we still get A. Okay, that's something to work on. But over here, we should see int. Yeah. And even if we suppose we provide a type annotation like T here, yeah, the type covers are currently wrong in the original spiral, but we aren't getting a type error, so we can be sure that X is T here. And what this allows us to do is to propagate the type information into the branch itself. Otherwise, it won't have possible. So what GADTs do, they act like a type case in the top-down segment. As long as you have an option, a specialized constructor like this, and then you try the destructuring it will actually take this type variable T, and it will know that it's I32 here, for example. And in fact, suppose we tried passing in an option. Actually, let's go to the next example. Because, okay, suppose we tried removing the sum case. Now, we can go to get rid of those constructors. And, sorry, let me just think of a better example. Okay, let's name them like this: option alt, option int. Let's make it some int, and we'll copy it above, and some float, and we'll name this float some float some int. And when this is an option t, you can see that we can destructure all of the cases. F32, I32. And we aren't getting a type error even though we are returning F32 here and I32 here, like we would with the regular union cases. Without GADTs, this would have been 100% an error in the previous version of Spiral. But because we know that we are actually unifying with T rather than with F32 or I32, with a float or an int, that's perfectly fine. I suppose we try changing the option to an int like this. Then what we're getting here is that unification failure. It's expecting an option I32, option int, and is getting a floating point option. So when we pass it in an integer option, it automatically knows that this float case cannot exist, and you in fact cannot even destructure it. The none case still does exist, so that's how it works. And this example that we have here is pretty much what the test here is testing for. It's pretty much identical. So let's comment it in. What this is supposed to show is that this union type is pretty much equivalent to something like this. I hope now that you've seen enough examples that you understand how GADT constructors work. In the regular option union cases, the constructors are implicit and can be constructed directly from the body, because you know that our T is the body, and you know that it needs to result in an option T. So there's no need to write it out explicitly. But with GADT cases, you have to put in the for alls and the body and the options explicitly. So that's basically it. Let's comment it in. Why is this giving us an error? Oh yeah, because we renamed it from T to QEA. And now, suppose we try compiling this. Build file. You'll see that we get two option types in the resulting code. And in fact, the other case is eliminated. This is TI32, T with a default integer. That's this. You'll see that it doesn't have a float case like a regular union case would. And when constructing B, it can only be a TF32. So the integer case gets eliminated. Suppose we tried adding something like C. And we can either leave it like this, or we can just make it for all x equals t of x, which is pretty much the same thing as just writing this. Suppose we tried compiling this. We're getting an error, which is a compiler error that I'll need to fix. So I guess the constructor isn't being correct, and I'll fix that later. But basically, it's supposed to be equivalent. Let's put in the GADT case for now, like this. Oh my god, we're still getting an error. Oh yeah. It's not that this is incorrect. It's just that I forgot to put in the other case. CA And this is here is just so I can hover over it and see what the variable is. Interesting that it's seeing this correctly and not giving me an erroneous metavariable. And then I'm going to look into that later. For now, let's build this, and what you'll see that now this has the C case. So yeah, basically this is how GADTs work. And what this will allow us to do is to write out graphs like the ones in the machine learning library. This is how the graph is going to look like with GADTs. Like the map, instead of being the thing that it was earlier, which was, let me show you. Where is it? I mean, it's at the top. What am I looking? We have this map here, and can I split the view? There's GADT. You'll see that the graph here only really works on something like two-dimensional tensors. And this map operation needs an existential, and if we wanted to write out a tensor explicitly, we wouldn't be able to specify the return type in the constructor. I mean the range of the constructor like this. Instead, this is just returning graph T explicitly, and we have to work within these limitations. But now with GADTs, we can write out pretty much any type, just like we would in a regular function. So we have the for all dim t, which and the dim isn't present in the top level variable anywhere here. So that gives us a lot of expressive power. I mean, existentials, you already know what they are. This is just a map function, but the input is now different. We know that we are getting in an input which is a tensor, and it's also outputting a tensor input. So that will be very helpful for what we're going to do in the future. The raw map, we know that it's okay. It's expecting maybe a two-dimensional input tensor. We could also change this so maybe. Actually, sorry. This two-dimensional tensor is part of the previous output function, and this is the actual input, and it's taking an arbitrary dimension. And this is what will work in terms of, like, now we have zip. Previously, when we implemented zip, we had to pass in something like a function like this, just so we have some connection with the output. Otherwise, graph tree could, otherwise these two zip nodes could pretty much be anything. Only by having something that is connected to the return type can we actually properly type this. But now we don't even need to pass in this function which acts as a proof. We can just specify the function like this, like for all AB, graph A, graph B, and it returns a pair of graph A and graph B. And sorry, this is actually wrong. What I meant to do was do this. Tensor dim. Yeah, now we pretty much know that this is supposed to zip the tensors. And previously, writing that out would have been impossible. The best thing we could, the closest thing we could do here is do something like write out a constructor, like zip Okay, for all dim a b. Okay, let's and then what do we do? A tensor dim a, b tensor dim b, tensor dim a b b. And we also wrap this in a graph. Let's see, graph. And how would we implement this? Something like a zip. I mean, we couldn't even implement it with this particular zip node. We need to somehow change it to a tensor. For example, let's see, tensor dim. Now, where exactly do we get the dim from? I guess we could make it an existential. Tensor dim. And yeah, now we have to pass in the entire function into it like this. Like, suppose we tried doing an alternative approach, like something like tensor dim a, tensor dim b, and what exactly should the output type of this be? Because now this t can pretty much be anything, any arbitrary value. And we could do a zip like zip ab. Why is this not correct? Oh yeah, it needs an existential. Exist ab, so we have to put in exists. And this is now wrapped in an existential. But the real problem would start when we start doing the passes for this, because now we have this zip t, and it has a bunch of existentials, and that isn't in any way connected to the graph's output. We have this model t top, and we have this graph t. Okay. Yeah. Basically, okay, you can hopefully get what I mean. GADTs increase the expressiveness of what we can do with unions significantly. And yeah, from here on out, what I want to do is maybe just go over what I did during the programming session, the one in the previous video, because all the audio has been lost. And so has most of the wisdom from this. I'm not sure what the audience for this is, but other people working on programming languages might want to know how I approached implementing generalized algebraic data types. And if you're doing your own functional language, you might be curious how you can go from a language with Hindley-Milner type inference to a language that has GADTs. Let me pause here so I can set things up. We'll resume shortly. Before we do a review, I actually want to go back to this example. I told you that this is a mistake, but it turns out it isn't. This actually isn't a metavariable, but a type variable. I got tricked myself. What's going on is that when you do a typecase, I mean, when you do an GADT and you destructure it, the compiler automatically inserts a typecase. And this type variable is actually the type variable that you get from a type case. So imagine if this was the bottom segment, and you wanted to get some information from this T. For example, we might have a case that you could have something like, let me do something that's not too stupid. Let's do A, B. Let's make it some pair. And let's say we only construct we don't even need to actually construct anything. We have some pair, and we have pair X. I know this X. Okay, it's okay. Let's construct it. Whatever. Let's make it something like. Let me pause so I can think of a proper example. I guess we'll just go with this, and you'll be able to figure it out. Here we have the some pair, option AB, and if we hover it, we see that we have these new type variables, and over here the X is clearly a pair. So if we tried maybe specifying it as something like int float, we get an error because it's getting a specific type and it has type variables. In fact, we cannot even access the type variables right here. Instead, if we wanted to maybe somehow access them, we need to make a local function like FAB. And then XAB, and then we need to actually do something with it, because this is one of the great benefits of Spiral, is that the type inferencer automatically fills in all the type applications for you. In this case, a bit of extra work would be needed to get the variables that get generated by the type case. And if we didn't have GADTs, then and only use those phantom constructors, like we have some pair T, and then we need to do something like in X, make some pair, and for all A, B, option, and this is a specialized type because we cannot just pass in anything. It has to be a pair. If you try passing in a record or a singular value like an integer or a float, we wouldn't be able to actually do this. Now, so we have some pair X, and now if you try accessing X, you see that it's inferring the type of X as T, and we don't have this. Like it's telling us, it's giving us an unification of failure. We're expecting a pair here, and it's just getting the type variable T. So if we wanted to actually somehow extract the stuff from X, we need to go into the bottom-up segment, and then okay, here the wildcards aren't allowed, and we have to do a typecase T with A, B, and great. And now we have the type variables A and B in here, and then we could do an assert that A or B. And this is workable, except now we'd be doing programming in the bottom-up segment, which is much harder to do than in the top-down. We don't get the benefits of type inference at all. We only get a bunch of type errors when we run the program at the end. I think the C++ templates work based on this system. And it's much worse than having GADTs. With the type languages, you might not be able to do open-ended type cases like these, but you can get some good alternatives. And that's all that I wanted to say on this subject. You just have to keep in mind that the compiler, the way they are implemented, the compiler will just automatically insert a type case for GADTs in the generated code. And in fact, in order to actually implement the GADT case, what I've added to the language is a type level type case. For example, you see this constructor here, but that's just for the constructor. In order to actually destructure the types at the type level in the partial evaluator, but what's also get generated is a destructor, and it kind of looks like alt and type case, something like t with int, and that returns an option int. Something like this is also implemented in the partial evaluator. Of course, I haven't implemented this on in the parser, so you cannot take advantage of this feature in user space. But it was necessary to actually to implement the GADTs in the language itself, in the language's compiler. Of course, as you can imagine, if this had something like a type variable for all, let's make it A, B, then this would look something like typecase T with A, B, option, and the partial evaluator would evaluate it like this on the type level. If for example this destructuring failed, like imagine if it's something like if the t is an int here, then what would happen in the partial evaluator is that instead of returning this option pair AB, it would return a void type. And let me show you directly in the partial evaluator. And we have this I void, and this is pretty much the only place where it's used. The partial evaluator checks whether the type is a void, and if it is, then it just filters it out. It doesn't put it in the dictionary when constructing the type in the bottom-up segment. And this is very useful. We also have, if you look at the other place where the void is used, we have this typecase. This is the type level type case. It's literally implemented like this. We have an unification function in the partial evaluator itself. It kind of looks like this, which is very similar to the one you see in the top-down segment, but it's a lot simpler. And it just returns a boolean whether the type unifies, and if it doesn't, then just get back a void. This is easy enough. And one amendment that I'd like to make, it doesn't actually unify it with T directly, but with option T. With option TAB. Yeah, so sorry, I forgot that, for example, if you had multiple type variables like something like X, then it would destructure it like this. Let's make it C. Option TX, and then C, and then C. Something like that. This is how the type level typecase works. Hopefully you understand a bit about the internal mechanics of GADTs now. In the parser, it's not very complicated either. Let's see. Block parsing, and we only needed to parse the cons operator. This one is for lists, but yeah, this one is for unions. And here you have the GADT case. It just takes in this. It just parses this colon operator, which is very similar to lists. Then it parses an optional for all. Then it parses the type. Then it puts everything together right here. And this is how the parser works. Previously we had just the vanilla and the none case, and now we have the GADT case. It took some work to get it to run in the parser, but that's about it. Let's see, is there anything... Did I add anything else here? I mean, I probably did, but if I cannot remember, then it's not really that important for you to understand, for your understanding of GADTs. I fixed some bugs in here, like there was a bug that the validation of patterns wasn't really recursing into the existential pattern. PatE exists. Let's see. Yeah, I mean, this part was definitely wrong. It wasn't doing proper pattern validation in the existential pattern, and we fixed that. And that's basically the only thing that is really important. Next, let's take a look at the type inference module. And what's new is this GADT links. This only gets triggered when when the unique case is a GADT. Let me put in a bookmark here. And before we proceed with the explanation, let me note the most important change in the entire top-down segment, which is in the entire inference module. Previously, the type variables was like this. I didn't have anything else except the scope, the constraints, the kind, and the name. In order to implement GADTs, we have to make it an option. We have to make it like the regular metavariable. So we had to add this option in order to be actually able to substitute it with something else, and that has a lot of implications for how the type inferencer works. But it ended up being a remarkably smooth transition. It didn't break the existing language design at all. It made some things a lot less efficient. More specifically, by that I mean the type covers. I'll explain why that is later. For now, let's take a look at everywhere the type variable is used. Okay, this is a very important change in the visit function. And why that is an important change is something that I have to show. Let's take a look at some of the references where this is used. For example, right here in this loop. And this is in fact the unification function. And when this visit is triggered, what it does is get rid of the metavariables in the current node. It shortens them. So let's go back to the visit. So I'll explain what this does right now. During the process of type inference, the type inferencer generates metavariables for pretty much everything ahead of time. If you have some expression like in x equals y, even before it type checks this y, it first creates a metavariable, and that looks like, for example, imagine we have some var. Okay, for type variables that metavariables, let's start them off with a quote, something like a, and that's how it looks like here. And if this y is something like an int, then it will get unified with it, and this reference will point to something like an int. It will get set to it. Like we'll have this time metavar, and it has this reference. At the very start, it's set to none, but it will get set to sum, and that sum will point to a tylit. Actually, not tylit, but typrim. And this primitive type will be in i32, yeah, in 32t. And this metavariable will basically just point to this node at that point. And suppose we call visit t on such a metavariable. When we have this, it's kind of complicated to actually do any unification. So we call visit t on this, and then it receives this metavariable, and it calls visit t mvar, and it gets rid of the comments. Like it just recurses on this, and this type metavariable, it sees that it's sum, and then it does some shortening of it, which I'll explain later, and it returns what's inside this metavariable. And this shorten function is not hard to figure out. It just calls the next. It also returns it at the end of the function. And if the links, and then it sets the link to this sum. So the end result of visit t will be that if it gets something like a metavariable pointing to an int, is that it will return an int. And it also does shortening. And what shortening is, if one metavariable points to another, which can point to another, for example with c, and then it has an integer at the very end, it will first shorten the entire path so all the metavariable, so the first metavariable points to an int directly. The second metavariable will also point to an int directly. And in the future invocations of visit, that will make it a lot easier to get the type directly, because this metavariable will just point to the int, and these two, they can, if they aren't used anywhere, they can even be garbage collected. And that's an important performance optimization. Of course, with type variables, things are different. We don't want to actually do path shortening on them. Otherwise, the type substitution won't be doable. For example, if you had actually a type variable, and this is a real type variable. Let's make it t. It's not a metavariable, but a real type variable. It doesn't have a code, and we destructure some GADT, and it points to int. And we have some metavariables pointing to, for example, a can point to b, which can point to c, which can point to t, and then this gets destructured into int. We don't actually want we don't actually want a to point to int. We want that to be returned from the visit function, this int, but the interest node structure should actually look like this. And that will allow the type substitution to be undone after the type inferencer comes out of the pattern unboxing case, and this basically implements that. This visit t, and let's see. Let's go check out the unification code next, because that's the other important thing for you to understand. Let's see. Yeah, this is it. Now the type variables have this reference thing. When we are unifying a GADT case, we need some indication for that it's not a regular unification, but a specialized one. And what's responsible for that is that we are passing in this option type. If this option type GADT links is sum, then this is a GADT that we are unifying. And it works very much like a regular metavariable unification. There is no need for scope checking or recursion validation. We just check whether the kinds unify and whether the constraints are right, and we assign b to a link. And unlike with regular metavariables, we also add this link to a resizable array, to a list that's inside this option. And that's important because after the partial evaluator goes out of the unboxing case, we want to actually undo the variable substitution in the type variable. So we have to put the link somewhere and then set it to none after the body of the pattern has been evaluated. And this is how the unification code works. It's pretty simple. You just have to be careful about these visits, that you aren't actually shortening everything, and things are very smooth. This unified GADT is only called in a single place, I mean directly. We have this unify that's pretty much called everywhere in this module, and since it's not a GADT case that's being unified, we pass in the none here. When this is none, this type var case will just get skipped over, and we'll get a regular type error instead of the type variables being unified with something else. So let's see, where is this being called? It should be called in pattern unbox. So let's take a look at that next. Yeah, here we have the pattern unbox. And now, unlike before, we're actually checking whether the union case is a GADT. And as you can imagine, this is this information, whether the type is a GADT, this is provided in by the parser. We just put in a boolean whether the union case is a GADT. Okay, ignore these two comments. This stuff here, you basically don't need to understand. What we are doing is just getting, what we are doing over here is just getting the global ID of the nominal being destructured in pattern unbox. And over here, we're just getting, what's this? Whatever. I mean, okay, this one, you can figure out basically what it does based on the errors. I have no idea. Oh yeah, I remember why this was done like this. When you encounter a pattern unbox case, the metavariable, I mean the variable that you're trying to destructure, can be annotated. And if it's annotated, I think maybe you'd go into this case. You just get the global ID of the nominal being structured, or here. But if it's not, then it might then it will try to infer it directly based on what's already in the environment. Like for example, I mean this is such a mess, but suppose we had an option type like this, and then we had in f function sum oh yeah, let's make this a regular option because it's easier to unify with something. GADTs will have to be annotated, but over here, because we know we have this sum constructor in the environment, even though we don't have the type variable annotated, because we have the constructor, we can infer what the type of the type variable is. It may turn out to be the case that, for example, we have a different stuff with, for example, we have other option, and which might also have the T case, or it might have some like QEA, and then it might be problematic to destructure this. But if you provide a type annotation, sorry, if you provide a type annotation like a option and then match x with, can't forget the equal sign, you'll see that it's actually destructuring the proper thing. Like this is an option A and not the other option T. So that's a little convenience, just what these cases take care of. You don't have to wonder too deeply what this HO index or HO fan are. All the functionality of the pattern unboxing is actually in the assume function, and the first thing it does is get the nominal body and the nominal variable list like right here. Then it destructures it, and from the body it can see that it's a tie union. If it isn't, but if it's something like a regular nominal, it will give you a type error. The type inference for regular unions in this else case is very easy. It just substitutes the. It takes the body and then it gets the actual forals used in the code and substitutes those type variables in the body of the union type definition with the type variables in the code. That's what this substitution here does, and then it recurses in the type inferencer, and does the type inference for the body of the union case. The body of the union case is just this stuff inside the union case, between the parentheses. This part unifies the variable coming in By that I mean this variable here with the union itself, and not its specific constructor, but just the union itself. Or here, I mean, that isn't necessary because we already have an option annotation, but until it actually unifies it with the constructor, it won't know whether it's correct. So that's necessary for both the GADTs and the regular unions. This part here, this is where we add the types. This is where we add the hover types. In fact, in the previous version of Spiral, we only had something like a resizable array, but now we are doing a lot more here, and we're going to go into it. Why having GADTs actually slows down the entire language. Previously, we didn't need to do this term substitution here. We just added something like this. And this is a lot more efficient. Now we have to do term substitution, which iterates over the entire variable. I mean, since I started explaining, I might as well explain to you what this term subst does. I explained what visit does earlier, and the term subst does pretty much the same thing, except it instead of just visiting the current node, it does that for the entire type. And as a result, it constructs an entirely new type. For example, the visit would only, if you had a type variable like A links to B, visit would shorten this, but you might also have something like C equals int, and this is a pair of D equals float. And visit would only shorten that to something like, it would first shorten the initial node to this, and that would be it. I mean, it will return not the metavariable, but this. But this entire function, term subst t, you can see that it's calling visit t on every node, so you know that it does at least this much. But what it will also do is return everything inside it. So it will return int. And this is very much necessary when you have when you are dealing with type variables. What we do need to do this for type covers? For example, suppose we added this entire thing into the resizable array in covers. For example, you can see that we have the hover types, and this is a resizable array, and we are adding stuff to it. We are adding a range, which is kind of like the key, and we are adding the type. You can see that this X has type T, which is the node for the spiral types, for the top-down types, that is. There are much of other ones in other stages. And previously this wasn't necessary, and we could just put the type node as it is without having to do this term substitution. But now we do. And the reason for that is because it's possible to have let's assume we have something like a type variable t, a metavariable pointing to a type variable t, which gets unboxed into something like int. And suppose we put in this type into as it is without calling term subst in hover types. What would happen is that this type would get passed into the unboxing case, in the body of the match case. It would get added to the hovers, and at the very end, at the end of the body, the type inferencer would return from that and undo this link. So after this link gets undone, because it's no longer unboxing a GADT but outside the match case, this t would get set to none, so it would just be this again. And unfortunately, the tag hovers inside the unboxing case would be wrong. So it's necessarily to actually do this entire substitution ahead of time. So if the type hovers are pointing to int instead of this thing here, then the type hovers would be correct. But now we have to do pretty much this term substitution everywhere, and that's a necessary evil. And it took me a while to figure out that we need to do this now. But thankfully, the top-down type inferencer isn't actually the slow part of the language. So even if we're doing this everywhere, it doesn't really matter. We do have a slight optimization, like let's see, it has substituted tvars. If it doesn't have any type. If it doesn't have any type variables with type substitutions, then it can do it a bit more efficiently. It will just put in the meta variable directly, and that will resolve the issue. But of course, unlike before, now it has to go over the entire node tree, so it knows whether that node tree for the types has a type variable with the substitutions. So that's another slowdown. That's basically the only disadvantage of having GADTs in the language, and that is that they make getting the types or the type hover slower. Now let me go over this. As you can see, we have to increment the scope. Otherwise, the metavariables outside that could possibly unify with the metavariables. With the type variables introduced by the typecase inside the body of the match case, inside the body of this pattern unbox. No, sorry, I don't mean to say the body of the pattern unbox, because the pattern unbox doesn't have the body of the pattern unbox is just another pattern, and the body of the match case is the body of the function or the match case, which we'll see elsewhere. What we're doing here is if the type is a GADT, what we need to do is extract the following variables: the body of the constructor and the specialized constructor. The specialized constructor is just this part here, and maybe this part here for the different type. It's just the last part of the function, and it needs to be separate from the body. We only need to do the structure based on what's inside the body. If we have a function like this, then what the type inferencer does is, or maybe even the parser, it just inserts a union type like this. So that's what it gets unified as. So we have the for rows, the body, the specialized constructor. And in order to actually fill in the type cases in a later stage, we need to pass this along. We have to pass in the current type. This is what will get typecased, in the correction of the type case, which is do we have a type? Yeah, this is basically the correction of the type case, and this will get destructured. This is what will get destructured in the body. The specialized constructor will get destructured. We need a list of foreign variables in order to actually know what to substitute in the specialized constructor, because we cannot just swap every single variable in type T with a. Sorry, I made a little mistake here. Instead of T, this should be option T, and then option. You can imagine the issue why we need the for else inside the constructor is so we know which variables need to be substituted with metavariables. We could have something like a type. Let's see. We could have and then okay, I'm a bit struggling to think of a proper example, but okay, just forget everything else. Imagine we also need to destructure something like Z or X, and those aren't a part of the. And I suppose those aren't a part of the constructor here. Then we don't want to turn these into metavariables by accident. That's basically all that it is. Just ignore. Just use our imagination in this case, because I cannot think of. I don't really feel like typing out a proper example demonstrating this. It's not that difficult to understand. Oh yeah, for the GADT cases, it's not necessarily the case that it's sorry, forget that last sentence. I mean, this is just a little hack, because what I found when I was doing let me get rid of all this, I'm tired of it. Let me just change this to QEA. Okay, and previously this was an option, and without that hack, what would happen is that I'd hover over QEA, and instead of I hover over A, instead of this type, I just get an union type, something like open and closing parentheses. And while thinking about it, I realized that this was because there is a range conflict. The body gets unified with this range, and the type itself gets unified with this range. So the union type ends up winning out. So the union type in the body ends up winning out when looking for the hovers. It's just a little fix. Okay, the unified GADT is finally do the unification in the body of the pattern. Right now we are passing this resizable array, and this is the only place in the entire type inferencer where this is getting passed in. We are also passing the type that's coming in, because the type variables in it need to be substituted. and we are unifying that with the specialized constructor, and that's how it works. It's pretty simple when you explain it like this. One thing we did need to do during the session is pretty much rewrite the way the types are propagated. Previously, if you look at this loop function, we were passing the scope and the environment in a immutable fashion, in a functional manner. But we got rid of all the functional stuff and replaced the immutable maps with these dictionaries. They're only really turned into immutable maps once this function is done. I found that we had a lot of bugs due to not using the imperative approach, which is kind of unusual, but it depends on the task. So we implemented it like this: update env. It's only used in the when pattern and when exiting this function, which is for the inference of patterns. We're also returning these GADT links, and these links are, as I said, we need them to undo the effect of substituting the type variables. GADT type cases. This we need so the type inferencer can fill in the type cases in the function bodies and the match cases. So let's see, what else did we do? Now we made some bunch of other changes. For example, validate nominals. Right now, in contrast to the previous version of Spiral, both the regular nominals and the recursive ones are handled as in the recursive segment. We no longer have separate mechanics for the non-recursive ones. And one implication of that is that the nominal's own type is getting passed into it. So suppose we had something like QA equals int. Actually, let me name it SD. And we have nominal equals, let's say, actually I wanted to just demonstrate this. Suppose we try doing this now. It will get an error. Non-recursive nominals should not use their own type in the clause. Well, previously this would just capture this one. So that's one way the semantics of the language have changed compared to the previous version. But I don't think that this will get used in the much in the nominal. So I don't mind making this breaking change. Of course, since unions are also nominals, the same applies to them. ESD equals oh really? I mean, this should be a type error. Why is it not type checking them correctly? Non-recursive nominals should not use their own type in the clause. Yes, that's exactly it. But when we just put it in like this, we don't get a type error, and this is an error in the language that I need to fix. Let me pause here and I'll do it. The new Spiral version is out, and let's give it a try. Excellent. Now this is an error. The way I've been implementing recursion checking for regular union cases was in fact wrong. Let's get back to talking about the language. Compared to the previous video, I had to change this code a little. But it's just doing Mario checking. It's not really worth commenting on. Let's see now. This is where it's filling in the for alls. It's converting a type to a raw T expression, which is used by the parser. The way it works in Spiral is that we have the top-down level, but it gets the types inferred by it get turned back to the raw parser expressions, which are then passed to the prepass. The top-down segment is essentially a wrapper put around the partial evaluator, and I think this is pretty good design. Okay, first here we have the conditional, the for all words. Those get substituted here into metavariables. On the left comes the constructor, on the right the body. There's no need to comment on this too much. Let's see. Okay, here's how the match clauses look like. First it evaluates the pattern, it gets back to GADT links, GADT typecases, the scope and the environment. Then it evaluates the body of the match clause. Then it gets rid of the GADT substitutions. This is the array that is getting passed into the unify function. Then the GADT typecases get added with the relevant type. Okay, that's good enough for the top-down segment. And the top-down segment is what's really important to understand. In the prepass, the only really important part is basically this. And this is what creates the constructors that get passed into the prepass. You know, when let me open this. When you create this, then it has to do something like create a constructor, and it creates something like a equals QAI32 equals a. So I mean, it doesn't equal a, but it puts in the nominal. Puts in the node to create a nominal. So it may be in a maybe it could be imitated using nominal 8, and then imagine for a moment that we are programming this in the bottom-up segment, and then QAI32, and then comes the key, which is a, and we pass in the unit type as the value. And it needs to create a constructor for each of these cases. And it needs to create a constructor for the GADT. There is also the case for the union type. There is also a case for the regular nominals. We had to do a bit of factoring out in the previous video. Let's see. Let me just go over this briefly to see if anything, to see if I need to cover anywhere else. We spent a lot of time working on this and debugging it, but it's not really necessary to explain it too much. Now that we know the design, we could do it very quickly if we needed to do it again. What I've explained might seem simple, but it's actually took me quite a while to figure out how to do this. Even so, right now I'm very good at this. So the fact that I did GADTs in like a week is pretty miraculous by my previous standards. Let's see, why do we have change? Sorry. I think this is the latest change. Let me just pause a bit because my keyboard is acting wonky. Now comes the last part, which is the partial evaluator. The typecase is pretty easy. It just goes over all the typecase cases and looking for the first one that unifies. If it's a metavariable, it will put the variables in the relevant slots in the environmental array. Let's see, metavariable. Oh yeah, it will just store the type into the array over here. It also, okay, I'm not going to go too much into what this is doing, but rest assured that it works. Here we have the T union, and previously we didn't have this part, but otherwise everything is the same. I didn't have to. I had to change the partial evaluator frighteningly little amount. Initially, what I thought that I'll have to change all the pattern unboxing cases. Let me just find them. There are a lot of them. Okay, this is type. They are in term. Let's see. Oh, here's the unboxing case. And this is the node that gets hit when you do a match statement. And the main problem isn't just the simple thing. The problem is that there are like 4 of them. Here's unbox 1. This is the unbox operation. It will unbox every single case in the union iteratively. Unbox 2, that's for equality. Because if you're checking for something like equality and you have fuck. I keep running it by accident. Let's see, match AB with imagine something like a case like this, and you want to check it for equality. It's possible to compile it a lot more efficiently than, I mean, not a lot more efficiently, not in today's version of Spiral, but it's possible to compile it more succinctly and efficiently if you first just check the tags for A and B, and then check the tag of the first one. For example, if A tag, this is just pseudocode. And forget that I'm just writing it right here in the middle of this. Then you can do, and you know that if A is this capital A, then you know that B is also that, and you can destructure it. And the problem with this unbox 2 is that it has a bunch of cases that need to be partially evaluated. For example, this is when both of the cases are known at compile time, and then there's the case when the right side is known only at runtime, but the left at compile time. And finally, when both the cases are only known at compile time. I thought that I'd have to hack all of this in order to enable GADTs. But it turns out that it's possible to just eliminate the unused types, unused cases from the union type completely by the time it gets to this point. And it isn't necessary to change anywhere here at all. That was simply majestic. I thought that the partial evaluator would be very hard, but it turned out to be very easy to deal with. Also, the fact that we now have type existentials cut the work that we needed to do for the GADTs in half. Existentials are pretty much half of what GADTs offer in other languages like Haskell and Camel, and as well as the dependently typed languages. And the fact that we've been able to factor this feature into two separate ones, which are existentials and specialized union constructors, makes our job a lot easier, because we can implement the existential as one feature and test it in isolation, and the specialized constructor that make GADTs as a separate feature and test it out as well. If you tried doing it all together without even understanding that GADTs can be factored into existentials and specialized constructors, rather that we needed to show existentials into GADTs somehow, then yeah, this feature might take us a whole month, and it would be a lot more complex to deal with. And I'm feeling very proud of this, which is why I'm doing this review. This feature is very big in terms of its impact on the language, and I'm not sure whether the Spiral language will get a similar feature, a feature of the same magnitude ever again. So I do regret deeply that we lost the audio in the previous video. This work that I did on GADTs might be some of my best one on the entire language. Though I'm proud of the language itself, of course. I don't know, nobody's watching these YouTube videos, I think, but if I could send these videos back in time to myself from 2016-17, he'd be very impressed, and he would find them very useful. So I guess that's my real intended audience. My intended audience is the me from a decade ago. They're not very useful to me directly, and who knows, maybe there will be somebody who's interested in the benefits functional languages provide, and he'll stumble upon these videos. So maybe they'll be useful that way. I actually had to pretty much reinvent the entire field of partial evaluation on my own. I didn't actually, during the implementation of the Spiral language, I didn't read any of the academic papers going out on this subject. Instead, I just let it develop organically. So, for that reason, I don't have much of a high opinion on academic work. Maybe doing it on YouTube like this is better. Who knows, maybe in the future researchers will be making YouTube videos like I'm doing now. To be honest, I don't want to be a researcher. I'd rather make a machine learning library and make a poker bot and then absolutely crash the online gambling dens. That was my original goal from the start of this journey, but I've gotten very sidetracked into working on the language and all the other things. Also, I'm very disappointed that better algorithms didn't come out. And I thought that instead of GPUs, by now we definitely have novel AI hardware. But so the companies working on AI hardware are a massive disappointment. The only company worth putting our trust into at this moment is NVIDIA, as weird as it is for me to say that. NVIDIA is the only company which is really selling affordable hardware to hobbyists. Take a look at Tenstorrent. They're releasing some garbage that's very marked up and calling it a dev kit, as if people have infinite time on their hands to play with their trash. Honestly, with the release of Grayskull, Tenstorrent went from being my favorite company to being my most hated company. They completely pushed me into the hands of NVIDIA. Who knows, maybe in the future there'll be more worthy companies working on AI hardware, but the The current crop is so incompetent that I've lost all faith in the hardware crowd. Also, the hardware engineers are really shitty programmers. They kind of think they're in separate domains, but they're not. Hardware design is pretty much programming, just in a different guise. It's a very low level, but it's not really a completely different domain. I think maybe in the future, in the post-singularity era, we'll be programming nanomachine fogs. So maybe in the future we'll be able to do things like make cars out of thin air simply through our programming abilities. Saying it's a different domain is just a cop-out. They have really bad tools. And my favorite saying and my motto is that it's easier to get a better tool than a better brain. If you remember one thing about me, remember this saying. That's why I worked on this language for so long. I guess we'll end this video here. It's been long enough. In the next one, we'll start work on the machine learning library. We'll throw away most of the work. I mean, we won't throw away any of the work actually, but we'll change the graph node to the new format and bring in the old stuff, so it matches well with the new one. We'll be able to apply tensors, take views of them, zip them, and we'll be able to do all the compile time operations that we need to implement the machine learning library. So make sure to like and subscribe, and we'll see you in the next video.